So next, let's talk about stating hypotheses. So a significant test starts with a careful statement of the claims that we want to compare. So we're going to have a null hypothesis and an alternate hypothesis. So the claim tested by a statistical test is called the null hypothesis. We're testing that claim. And often our null hypothesis is a statement of no difference. So it always has, I don't know why my pencil's not writing, always, that's weird, always, now we're working, has an equals sign. That's a nice way to remember it. It always has an equals sign. The claim about the population that we are trying to find evidence for is our alternate hypothesis. And the alternate hypothesis is one-sided if it states a parameter is larger or smaller, so like greater than or less than, or the null hypothesis is two-sided or two-tailed if it has a does not equal sign. So in our sweetness example, our null hypothesis was that our mean equals 0, and our alternate hypothesis was the mean is actually greater than 0, meaning that sweetness was lost. So this is a one-sided test because we're interested in only whether the cola lost sweetness. It would be two-sided if we were interested if there was like just a change in sweetness, but that's not this hypothesis test. Let's look at what would happen though if we did have a two-sided or two-tailed example. So, does the job satisfaction of assembly workers differ when their work is machine-paced rather than self-paced? So we're going to assign workers either to an assembly line moving at a fixed pace or to a self-paced setting. So this would be an experiment because we're having like an effect. We would have all the subjects work in both settings in a random order, and after 2 weeks, we would test their job satisfaction. So this is a good example of a matched pairs design. The response variable is the difference in satisfaction scores for self-paced minus machine-paced. And the parameter of interest, in mean mu, would be the difference in the scores of the population of all assembly workers. So here, our response variable is the difference in our satisfaction scores, and the parameter of interest is the mean mu of the different scores in the population of all assembly workers. So we need to set up some hypotheses, right? So our null hypothesis says that there's no difference in satisfaction scores between self-paced work and machine-based work, right? No difference means if I subtract them, I'm going to get a difference of 0. So I'd have mean equals 0. The authors of this study wanted to know whether the two work conditions have different levels of job satisfaction, not whether one was greater or less than. They didn't specify the direction, so this is two-sided, meaning my alternate hypothesis will be that the mean doesn't equal 0. So, first off, warning, okay? The hypothesis should express the hopes or suspicions we have before we see the data. It's kind of cheating to look at the data first and then frame your hypothesis to fit what the data show. You need to know what you're looking for in the beginning. So now that we have our null and alternate hypothesis, how do we know the strength of either of these hypotheses? Well, that's when p-value comes into play. So our null hypothesis states the claim that we are seeking evidence against. And the probability that measures the strength of evidence against the null hypothesis is called a p-value. We want a high p-value. So we calculate our test statistic, which is calculated from the sample data and measures how far our data diverge from what we'd expect if the null hypothesis were true. Large values of the statistic show the data are not consistent with H naught, right? And then we would reject our null hypothesis. The probability computed assuming H naught is true that the statistic would take a value as extreme or more extreme than the one actually observed is the p-value of the test, okay? The smaller the p-value, the stronger the evidence provided by the data. So there's like a saying, if the p is low, you reject the HO, the HO, the null hypothesis. So small p-values are evidence against H naught, right? Because they say that the observed result is unlikely to occur, right? If I have a small p-value, right, if I got an outlier, and the area over here is 0.05, right? So 5% likelihood it occurred by chance, that's when we would reject our null hypothesis. Large p-values fail to give convincing evidence against H0 because they say that the observed result might have occurred by chance if our null hypothesis was true. Next, test of significance assess the evidence against null hypothesis. If the evidence is strong, we can confidently reject H0 in favor of the alternative. Note, there's only rejection, no acceptance, only rejection in statistics, right? So if we have a small p-value, we reject our null hypothesis and conclude our alternate hypothesis. If our p-value is large, we fail to reject our null hypothesis and cannot conclude our alternate hypothesis. There's no acceptance. We never accept. Never accept, only reject. Okay? So this textbook says there's no rule for how small a p-value we should require in order to reject our null hypothesis, and that it's a matter of judgment, but I argued it should be less than 0.05. 0.05 or 0.01. So you could reject it at the 0.05 significance level or the 0.01 significance level, right? We can also compare our p-value with a fixed value that we regard as decisive. We decide that's our alpha. When our p-value is less than our alpha, we say our result's statistically significant. I think your alpha should be less than 0.05, less than or equal to 0.05. So if our p-value is smaller than the alpha, we say the data are statistically significant at that level of alpha, or we also call alpha our statistics significance level, or the level of significance. So in the next video, we're going to go through the steps to test for significance and work through 2 examples.